So we're halfway through the class, actually. And while that may seem daunting, like, oh no, it's all been a mess, I want to stress to you that I'm really going to shift the whole, I'm shifting everything kind of halfway through right now. So if I were to summarize the first half of this class, this onslaught of all the crazy lectures I've been watching, really I'm trying to get, I really was just trying to get across sort of a couple things, right? So for the first half of the course, right, I wanted to write, the idea is I showed right, this is what I showed the Newton's second law, that our working equation for motion for fluids. And importantly, what was more important than actually just the equation, right, I really just wanted to show, right, everything that went into it, right, the assumptions that we use to derive them. And there are a couple geometrical ones and like continuity and continuous function things, et cetera. But that's what's important about the Navier-Stokes, I think, if you want to become an expert at these things. Is yes, you can always write it down, but it's better to really know why why you're writing that equation down. So that's really what I started that for, was I wanted you to see, the Navier-Stokes equations come about from asking questions of how on earth does fluid move around a body. Okay? And then with those equations, right, they're too hard. Even for a computer, they're just too hard. The full three-dimensional ones are extremely difficult. You need a lot of computation power. They didn't have computation power back in the day, but that's a big takeaway. It was hard to derive them. It's hard to write out every term of them. So appreciating that difficulty. Really, I was just trying to get that across. All right? So since they're too hard, we have to then make we then have to simplify this thing even further. Then really I showed a bunch of examples, right? I just burned through a bunch of flow problems, right? Right, this is what the most important thing. We did the Rayleigh instantaneous plate. There's oscillating pressure in the fluid. There's internal flow, the Laplacian things, etc. Well, they're really all coming from this. So you saw a bunch of examples. Right? I really just listed a bunch of examples where we just make some assumptions that simplify down this incredibly difficult equation. Now it's Navier-Stokes. I'm writing F equals ma, but hopefully you remember the vector format of how we are talking about everything. So I just exposed you to a ton of different ways people simplified this very complicated differential equation into either one or a set of differential equations, or a simpler partial differential equation, a simpler ordinary differential equation, and then they can get at its solutions. And I iterate this again. Sort of, this is really all it is. Because after you do this part, right, the output of this, right, is a simpler PDE or an ODE. Right, a lot of work to make the Navier-Stokes equations, where it all came from, what is a Newtonian fluid, sort of really pinning down what those things are. Maybe you have a better appreciation of what they are. And if you don't now, you can always look back and you can always try to focus on that importance I'm trying to stress to you. And then I just showed you a bunch of examples. Okay, take that thing, make some assumptions, and get simpler PDEs or simpler ODEs. Right? And then after this, right, this is just, people love doing it. I think academics like focus a lot on it. But like a solution, I don't want to say blah, but right, it's just sort of, math, right? It's just marks on paper, or it's just clickety clacks on a keyboard. But I want you to use your tools to solve those things, however best you can. I mean, we have so many tools now that can rapidly solve these types of things. But what's really important is not this step. What's important is this step, is getting at what your simplified differential equation is. So the idea was the first half, I'm just showing you a bunch of different ways people did that. So if you're lost on all of these examples I'm showing you, I think it's better to just sort of think about, like, what's the simple system? And then I showed you methods on how to, like, trickery or get at your solution, which is just nice to see. Certainly, right? Certainly people appreciate, like, analytical solutions or closed-form solutions. But we saw many times, sometimes that's not even possible. But just having your computer, like, do like a nonlinear integration method, right? That's still a solution. We could still learn wall stresses. We could still learn a ton of things from, stagnation flow, from the from the von Karman pump, right? We couldn't write that solution down, but given that simple solution, we can make a plot, and then that plot can tell you, something that's general for all types of flows. And that takes thought, too, because you then have to think about what do you want? And that's the hardest question, I think. I can't teach you that. What do you want? What do you want out of this differential equation? But getting this is all right. Doing this is just assumptions. That's how you get these simplified systems. You have to make some assumptions. Okay? So the only extra thing I've sort of done for you scaling is a methodology. Let's say method. Scaling really is a method to come up with these assumptions. So certainly people are having difficulty with that because they've just never seen it before. But really, this stuff is governed in fluids because, you can make an infinite number of assumptions for those Navier-Stokes equations to simplify them down. But if you use the scaling method, it's just a bit, right? It's a more patterned way to do it, right? And everything that goes into scaling, right? It's the idea of where do the scales come from? Here are my scales for my problem. And really the idea is that the scales come from, like, previous knowledge of the flow before it starts happening. So that's why it's a good method to come up with your assumptions, right? Because the scales come from, your geometry, right? They can come from initial conditions, right? Or boundary conditions. And there's other ones too. I mean, besides the scale, right? It's also sort of relevant physics. All these things that there's no way for you to actually tell the computer about that are things that define a scale. So mathematically, I can take, like, me defining a problem, and I can insert scales into this full-blown equation, and then that can rigorously let me arrive at what the correct assumptions are given my problem. And if you do this enough, then sort of this simplification thing should be pretty quick for you. But you just have to do it more and more and more. So this is probably the new thing you've probably seen, right? Before, maybe the simpler PDE is just stated for you, or the simpler system is just stated in your textbook. But there's this thing that we're doing where we're scaling things. It's really substitution into some derivatives, and you make small terms, and you say that doesn't matter or that doesn't matter, because I know that number must be really small. Pretty cool stuff, I think. It's certainly not intuitive, and it certainly seems like a magical trick. What else am I trying to get across with the first half, right? Besides just getting at the solution, right? Besides just actually being able to write down the solution to ODEs, right? I'm sort of always, right, the major goal in all of fluid analysis has always been one thing. We have always been motivated to answer one question. What is the velocity field? Maybe not even what is. I think what's too restrictive. So how about something lighter? Really, we're supposed to characterize this velocity field. Sometimes you can't get a solution, but you could say something about it. So this function, this vector field function, is governed by the Navier-Stokes equations. They're really complicated. You can't solve them. But this function, right, the velocity field is defined, right? It's defined in terms of the Navier-Stokes equation. So while you don't know what this function is, what we do know a definition for the function, and that is, right, it's the function that solves the Navier-Stokes equations. So if you want to find simpler velocity fields, you do this simplification method, and then you find like a u of y or u of y of t. It's sort of like it's a tiny little part of this velocity field, let's say. I mean, it is. But what characterizes the velocity field is the Navier-Stokes equations. So for a simplified model, that's what I want you to have really appreciated, right, that this is the big takeaway, I think, of the first half of the course. I said it a bunch, but sort of just that. Differential equations are a way to define a function. So really formulating that differential equation is the solution. You going about numerically solving it or actually writing out the analytical solution, right, are extra steps to represent it certainly in a different way. Not to say it's not worth anything. So in that sort of ending, I could have just stopped at that. I could have just stopped at okay, here's a simplified system. I'm done. I'm going home. I didn't do that. But just appreciating that we always had three avenues to go towards, right? You could get the simplified system, and then you do solution methods to it. Like in your homework, you could do numerical methods to get that solution. Sometimes it's linear, so you could write it out. Sometimes you'll know my favorite solution is late to the next lecture, which I love. But you can just attack it different ways. And why do you attack it? Why do you want the solution? And that's really this goal of right, if you can write down that velocity some way, meaning you've really solved it. What you've done is you've mapped now your initial conditions and boundary conditions to the solution. So it's hard to appreciate what you're doing when you're doing this solution type stuff. But if you can somehow, this could be a simplified v, let's say that, right? So this could be like a u of y. It could be like a u of z and t for oscillating flows, right? It could be, right, a u of x and y. You know, there's tons of different components that we're solving. It could be like a stream function, right? What does a stream function do? We went over that. It goes over a u and a v it gives you. It could be an ideal flow. You know, potential flows. All of these are sort of simplifications for what that velocity field was. And all of these functions of differential systems, they come with initial conditions that you set and boundary conditions. One of them is given to us, no slip. Always going to be given. You always have to state it. No relative slip. If a wall is moving, it has to move relative to that. So that one's almost, I sometimes think of it like not too much like thought for you, because it's always just state no slip. And then there's a zero shear boundary condition, which means it's symmetrical flow. It's not really true. I don't believe it too much. It's totally an idealization. No slip is always a better one because it really has to be true. But importantly, right, when you write these things out, when you write these things out, you write down a function that has all the information of the boundary conditions and the initial conditions and tells you what the solution looks like. So that means you now know everything, right? You now know a way to map any initial condition or any boundary condition, any way you set up the problem, and you would now know the future. I don't have to rerun any sort of program at all. You could just write it down and you'll be able to see it. So that's sort of the goal. That's always the goal of writing down an analytical solution, or even an approximate one, is that you have that ability to do that. Some people don't care about it anymore, but sometimes it's a bit easier to do, I think. Certainly the power of it. OK. So I did that because I want to kind of close this first half where I just do a bunch of examples of flow problems. I'm actually going to do one more. I'm doing the Jeffrey Hamel flow next class, which is my absolute favorite flow solution. It's my favorite fluid analysis ever done. And I like it because it really has every single method. Everything's in the Jeffrey Hamel flow, I think. You can just keep going back to that solution. And that's also, I'll talk about that too, how it's nice to just, it's really nice to just sort of like pick a problem you like and just look at the solution, rederive it multiple ways. Pick your favorite one, just work on it every single day. That's what I do with Jeffrey Hamel. I just resolve Jeffrey Hamel many, many times, and it's pretty fun. Right? So it may have been rough. I may have burned through way too many examples, but the idea is I hope you just got across that general feeling and that general idea of purpose that with this fluid analysis stuff, we already know the Navier-Stokes equations. You make one big simple assumption. You say incompressible flow, always pretty good. Why do we say that? Because you have to approach Mach number like 0.3 when that's going to happen, you know. And then from that, hope you also appreciate what I was really doing is I was like killing terms. Right? You're creating a simplified differential system, and now that governs the flow. And then the idea of scaling can get you there always, where you just look at the geometry or initial conditions or boundary conditions of your problem, and that lets you sort of have a method of actually writing down what are appropriate assumptions. So we're going to, so get out of the way, let's get on with this lecture. Right? So today we're changing perspective again. And I want to talk about the vorticity view. So, right, before I was always talking about this vector field, the V. So this is sort of an auxiliary vector field. And you get it by taking the curl of the vector field. So it's sort of I'll get through that later, but then appreciate that's what we're doing. This is called the vorticity field. This is the velocity field, the thing we've been talking about for 10 weeks of trying to get at. What on earth is this velocity field based on initial conditions and boundary conditions for a problem? If you have that velocity field somehow, you can take the curl of it and you get a vorticity. But these are related. And there's a relation that's Cree. So this is called vorticity. Vorticity. And this is called velocity. I think that's why they say vorticity, velocity. They want them to rhyme. I don't know why. It's certainly related to vortex. I don't know why they call it a vorticity. So, we could write down we're writing down the equations of velocity. We have Navier-Stokes equations, a bunch of analysis. So very quickly, this whole lecture is about well, what if I was trying to get at what this vorticity field looked like? You don't know what it is yet, but that's the idea, right? Right. 10 weeks of just thinking about what is the Eulerian velocity field look like? What do the Lagrangian paths look like? And then you do analysis, you make simplified systems to pin that down. But this is all about linear momentum, right? Something going in some line. Vorticity deals with spin, deals with angular momentum. So angular stuff is always the ill-behaved stepchild of physics. People don't like it. It's hard to understand. People just throw it away and forget about it forever. Certainly, I don't like to think about rotational stuff because it breaks my brain. So I'll just break your brain too for this lecture because everyone's got to do it. And it's also spoken a lot about, right? So the language of fluids, if you go to a conference, something like that, or anywhere, right? People use the concept of vorticity to describe a flow. So hopefully I prepare you just to understand that language maybe of why they would do it or what to think about when someone's saying, the high vorticity in this fluid, or there's not enough vorticity over there, so it couldn't possibly. But that language is what we should be well posed in understanding. And it's not easy. And I think it really comes from people solving velocity fields on computers and then calculating vorticity, then looking at that. I think analytically it's pretty, never mind. OK, so to get there, let's recap on what the velocity field is defined by. Again, remember, I'm always saying a way to define a function is to define it in terms of a differential equation. OK, so this, incompressible-wise, right, it had this definition. If you don't remember what this capital D is, right, you really should memorize it or understand it. Well, not understand, but at least just memorize what the terms are, right? I understand it's notation, so it's why don't just write every component? But at this point, you should realize I hate components, and I think symbolic stuff is better for reasoning. I promise you, I think it actually is. Okay, so this is the Navier-Stokes equations, and it has and for incompressible, we also have this relationship, right? When is this true? When is this true? Don't friggin' say don't say when density is constant, right? We're advanced now, so this really is for when this is happening. And I showed that through non-dimensionalization. The idea that this is what drives that supposition, incompressibility. Compressible flow is a flow statement, not a medium statement. OK, so this is what governs the V. Has a bunch of terms in there. It's good that you understand these terms, right? So this term right here, here is your inertial term. Right? The inertial term being the MA term, right? So this term in the equation is saying, right, the resistance of the fluid's resistance to motion, right, or its tendency to keep moving, right, if not acted upon by a force, is this expression right here. It's this idea that if you have a bunch of, a water hammer has a bunch of inertia in it, right, or if you have a flow moving extremely really quickly, right, even if you remove all forces from there, there's this tendency to keep moving. Okay, so that's governed by here, right? Here's pressure term. Always sort of rough, I think, because it's just and here's pressure. But this, I want to hopefully understand that these you've seen before. There's a rationale of why these pop up. And then there's this term right here, right? And these are viscous forces. There's a viscous force term. And what is the viscous force term? Well, it came about from like the equations themselves. If it's incompressible, it's the idea that bodies or elements of fluid can shear and deform. Okay? So some use viscosity, density, material derivative, capital D. Remember what that is. I'll just write it down. Remember that this material derivative is an operator that we defined earlier. Partial T plus the vector field itself. And it's this operator. So you take this, multiply it on there. That's where nonlinearity comes from. Okay, boom, boom, boom. Here's all these terms. This is just a, right, so this is a gravity force. Importantly, you have to think of this as a body force, right, or a volume force. Is that there are these other forces that could always exist over here, right? You could have some magnetic force, right? So magnetic, right, or electrostatic force or something like that. These forces that act on volumes, not surfaces. The viscous force is a surface force. So it comes about here through simplifications and looking at control volumes, however you want to describe it. Right? This is just a conservation of mass equation. Here's a conservation of linear momentum. I don't like conserving linear momentum. I like to think about forces. But that's where this comes about from, right? The idea that you conserve linear momentum. All fine and dandy. So just to get it in maybe a form that looks far more familiar, because this doesn't quite look like what you're used to, I think. This is a directional gravity force, right? Because you could have any coordinate system you want, but this gravity vector is always pointed down towards the surface of the Earth. Provides an orientation for flow. So, right, I can write this and this. I can combine these in a way. I can combine these if I just put a z-coordinate here, where this is actually take the effect of a gradient of a potential function. Okay, so if that's the case, I can write the equations like this, where I've sort of redefined now my hydraulic head. This being rho g. Let's say a z force, if it is in the z direction. People write this g vector because sometimes it's not always directed in the z direction. It depends on the coordinate system. But either way, it is like this. So, right, the gradient of a scalar function produces a vector. So that's this idea of a gradient force. One other way to think about this is the gravity force, if you remember from physics 2, is something called a conservative force. Right? So it's path independent, blah, blah, blah. But so conservative forces are the result of a potential function. Remember potentials? Right? So you can redefine it like this. So it's sort of a little bit closer to maybe a little bit closer form-wise to something we've seen before. And now I'm just going to do another sort of thing. So I have this. It's a terrible scripty. So let's redefine again some change, right? Some derivative change, let's say. Right? You're taking some change in velocity. It's just a fancy definition of what change means. The material derivative is. So let's redefine another change. Let's redefine taking a derivative in a different way. Right? So this is where I say, let's call this like a superscript d. Like this. And I'll define this thing sort of related to the material derivative, but it will look like this now. And then I have a, and then I'll just also lump this on there. So here's another fancy change. This is a kappa, a script D, not a P or something like that. It's a script D, right? Also, I hope you remember that this too. This is kinematic velocity. Right. So now I have some new sort of definition of like taking a derivative now. I've just redefined this, right? So I have this negative here. Importantly, you have a negative sign as well. You wouldn't have a positive right here. Keep the negative because I know for a fact that viscosity is not a negative number. I've never been measured before. It'd be weird if there was a negative viscosity. Interesting conclusions if there are, right? It's a very interesting idea. Okay, and then this is a square operator as well. So it's the Laplacian, and there are properties of the Laplacian that obey directions. Right, they always will tell you the direction of change. It doesn't really matter. Right, so just the negative sign is important for this definition. Okay, so now in this context, now I have this sort of even simpler notation of what the Navier-Stokes equations are, or conservation of linear momentum. Per unit volume. So and this is sort of a key identifier too, because this gradient of my gravitational potential, because this is the pressure force right here, and then here's some conservative vector field. It could have the gravity force in there. It could have a Hemholtz force. It could have a van der Waals force. Think of just all forces coming from conservative forces. So there might even be other terms in here. Let's call it, maybe a psi. It could be like a not gamma, right? It could be a ton of different superpositions of fields, right? Where this is a gravitational. This could be like Emag, right? This could be a van der Waal. Okay, you can just keep on lumping on conservative fields, which you can take a gradient of to then derive a force. Then it really does have the same exact form that you maybe have been used to, right? Because force, right? It's hard to remember, right? If you remember that, force is another way to define it is it's the negative of a potential u. So that's exactly what's on this side, right? You have sort of these force per unit areas per unit volume, right? You have this force per unit, force per unit area per unit mass. Okay, so it's sort of a norm, right? So it's some sort of normalized form of the gradient of a potential, the negative of a gradient of potential. So here's your force. And then, right, the dv dt is an acceleration. And that's really sort of, that's the importance of this pressure field right here. Because this is, right, it's a statement saying that, right, motion is prescribed by forces, or forces prescribe motion. Right? The idea that pressure prescribes, right, the idea that pressures prescribe some amount of motion occurring, or any motion that's occurring is the result of some amount of pressure or forces, the negative gradient of potential. And this is, of course, all happening in the case of linear momentum. Linear momentum. So all we've talked about is linear momentum. Right? I mean, Newton's second law is just that, right? If it's just in linear momentum that you're seeing, right? If capital P, I should not use capital P. Okay, script P. This is Newton's second law. The time rate of change of linear momentum is equal to the forces, or the sum of the forces. So, some fancier sort of, some fancier definition of what this change in time is, and then this v, you have to keep, right, you're kind of subtracting out the density, then multiplying through the other one. But they have similar forms, right, with that being linear. I'm tracking linear momentum with these equations. So sometimes I actually like just thinking about the equations like this, because you can kind of go, okay, so I have some fancy change. And then you can actually think about how this operator works, instead of the whole equation sets themselves. Sometimes pretty quick. But that's not good enough. Because in reality, what we should, right, there's another one, there's something also, and that's angular momentum. Right? big question mark. What about the angular momentum? We only talked about linear momentum. This idea that we also have a conservation of angular momentum for anything that we have. So sort of so that's really the stepping point to this vorticity, I believe. Instead of just saying, this is vorticity. Maybe I personally have never been satisfied understanding something if some professor at a book just says, like, this is vorticity. Not my favorite. So I try to at least come up with like reasons why. And you kind of look to just like in histories of how these things come about. They usually are just governed by some simple questions. Okay. So this is the problem being, right, and you remember when we did rotation, right, you have some body, right, maybe some surface, could be oblong, spheres, et cetera, are pretty nice to obey, right? So this is sitting in some space or region of fluid, right? And I have definitive ways, and I have a pretty good set of equations that describe everything in terms, right, everything in terms of this, right, linear momentum, or this linear velocity. So right, angular momentum is related to a angular velocity, right? So you could think of this as a linear velocity. So I sort of have in a limiting sense, I've defined this, and I really know exactly everything that's happening right there. And I've even defined it in terms of, right, the shearing and the deformations of this boundary that you draw around it, because this has to agree with a neighboring one. And so this is going to be the velocity at an x naught, a y naught, a z naught at a time t. In a neighboring sense, here's another linear velocity at a different point in space at the same time, right? So what? Right? So viscous. Right? The idea of viscous forces, they talk about like in this limiting sense of how these two little bodies have to agree. You can't store surface in the intersection of. You can't store energy in these intersecting surfaces. But there's also rotation that's occurring. So linear momentum is conserved throughout all the field based on these assumptions as well. But there's also, right, this whole thing can be rotating like this, right? And this one could rotate along like this. Essentially, my whole field could be a bunch of little marbles sitting in space. And you shrink the marble down further and further and further. Right? As I shrink the marble down further and further and further, I still have some point v defined in this direction, because that's what you're trying, in the limiting sense, trying to get at. But this rotation also has a vector corresponding to it, right? The angular spin about my coordinate system has a vector associated to it, right? So that's what the vorticity, right? That's what a vorticity is. But you can get, right? The idea is it is from certainly angular momentum, right? I mean, if you remember, angular momentum is this. It's called, capital L, let's say, cross product P. So I'm sorry, right, on this notation, and people, you've all gotten on me and how my notation is pretty bad, and I need to define things better on the board, so I'm trying that. So P's bad because we use P for pressure, but if we're going back to physics 2 right now, and you have to think of P as being, right, a linear momentum. Right? So think of P as being mass times velocity, not pressure. For now. I will go back and say now P, right? I will go back and say now P is pressure. But also there's something, right? So there is another hint that I can use P for linear momentum because, right, pressure is a scalar, not a vector. So a p with a vector on top of it is always going to mean linear momentum in anything you read. So, but I just pointed out. Okay, so that's linear momentum, and it has this issue that it's dependent on this r. Right? It's just dependent on this radius to the linear momentum you're speaking about, which is always the hardest part, I think, about this rotational stuff, is where on earth do I measure this radius from? This is the big issue of if I have a coordinate system and I put it here. Okay, so I'll say this was like my origin or my coordinate system number 1. You can have a linear momentum of this sort of thing right here, where this is my R1. Okay, and then the cross product between this vector to this center of mass, let's say, and to that linear momentum scaled up by the mass or the density now. And that would give you an angular momentum about a point. But strangely enough, right, you could make a different one. Okay. So just by changing this coordinate system, now you're changing the value of the angular momentum. But this is exactly the same as it's really just the difference, right? So we only look at differences, and that's what's right. That's the idea of a conservation thing. This is the difficult thing about angular momentum. This is like the heart of why I think it's rough when it comes to angular problems, is this idea that, a cross product is dependent on some way you measure it. Right? I mean, if I said an L1, same, right? This didn't change. Right? These don't end up being the same value because the R is different. But if you put the coordinate system at the center of mass of something, then everything checks out. There's a natural origin to everything, and things play nicely together. So, right, this is sort of the straight, right? So angular momentum, angular velocity. I've sort of gotten at. I'm trying to get at this idea that we have this v described by the Navier-Stokes equations, but there's this other thing that's happening where all my surfaces, there's some vector defined by this, and it's talking about the spin of like these objects I have. But if I limit them down and down and down and down, I shouldn't just the spin vector shouldn't just disappear. It's still there even though it's a singular point, right? Let me call this. Right, so what I'm sort of saying is that by shrinking this volume down and down and down in my limiting cases, right, that rotational vector that described that rotation shouldn't vanish. So on this idea of spheres, keep going with it. And that's one nice interpretation then of vorticity. So vorticity, right? An angular momentum of a spherical body. So this is now angular speed. Speed, right? If you haven't seen this notation before, this is the Euclidean norm. So this is just, right, the square root. So it's Pythagorean theorem for 3 dimensions. So, right, if this is a a vector, you'd take the sum of the square of the components and take the square root of that generalization. So that's what these bar notations are. It's the vector magnitude. So the angular momentum of my sphere, right, at the vorticity at that point, has its interpretation like this. It comes about just from how we were talking about things. But it is sort of strange of how to get across this idea that, you know, a way to calculate this vorticity is this curl of the vector field, right? This definition of why on earth the curl of this vector field should give you something about angular momentum. I mean, certainly here, right, you have this p, right? Certainly the linear momentum here, you have, right, the linear momentum is some, you know, position wherever I decide to put it in right here, right? We have a mass, so here's some mass of a volume, and then here is right here. So this certainly looks, you know, close to it. But then you have this gradient operator curling, right? This idea that this sort of, there's a mismatch going on right here. So there's a couple things we can do. I mean, this arbitrariness of this R where you measure from is what's strange. It's not too hard. I mean, no, it's not too hard. It's pretty hard. So one thing about cross products that may not be, you know, noticeable is this is really a rho and a volume, right? So let's say, well, capital omega is volume right here. So just exchange for mass right here. One thing about a cross product is this, if you don't remember, right? If you have A times, say, a scalar B, right, this is equal to this. It is equal to this. So if you haven't remembered, right, this idea of cross products, right, a vector cross product is the idea that, right, you do move around. You can move around this scalar is the thing to either be on the left-hand side, the right-hand side, or just completely outside of the product. If you had two of them in there, right, I mean, if you had two of them in there, I mean, essentially, if this is a scalar, right, the scalar can just hop around anywhere, and it has the same definition, is the idea. So while I put them while I put the rho omega over here, it could go outside. Okay. This is an angular momentum, capital L. Have this sort of thing, have this operation going on right here. Sort of last thing, you can divide out by the volume. Let's call it lowercase l then. Right? And this is now in a per unit volume, lowercase. Okay, pretty close, right? I have angular momentum per unit volume, having this r here just from the definitions I have. Right? How I'm defining things geometrically is where this is coming from. Okay, but getting closer, I think, to where on earth this is really coming from, this cross product with the v. Okay. And remember, too, what do the Navier-Stokes equations say, right? This is going to be think of this as so in terms of all the Navier-Stokes equations, right, you have this, right, this density value out front, and then when you divide out by any sort of arbitrary region, you're now talking about things on a per unit volume basis. So some things are certainly matching up now. I have an angular momentum per unit volume, and I have linear momentum per unit volume. This one, nice and well defined. I think I did right. We have 6 equations that govern everything about it really well. Just trying to get at this angular momentum one right here. So why do I go from this radius vector to this vector right here? And this radius vector is this idea that, right, these coordinate systems, right, has to be independent of the coordinate systems that you have. Right, for at any point in the region, right? I described how this, where I define my coordinate system, right, is going to change that value. But if you put it on the inside of any internal volume, right? So if I always put my coordinate system regardless of whatever coordinate system I speak of, then it should work out. So this is the issue, right? So while I do have free, right, I do have this range to have this r, the r is arbitrary. This is not. This is not arbitrary in the field because it talks about differences, right? So quickly then, I'm taking a lot of time on this one. Taking a lot of time on this one because it's rough. So move the coordinate system into there. At any arbitrary point now in this velocity field, say it looks like this now. Capital OC, if you can see that, right? So now I've moved this coordinate system relative to that origin or the center of mass of any arbitrary surface I put in my region of fluid, right? Now this vector can be defined by rotation itself. I mean, right, this concept that you think of this as some row operator. So it's something about, per little changes in x is what is defining the rotation. And that's what works out if you then think about, well, at any point as I shrink my marble smaller and smaller and smaller, right, if it has the same angular speed as I go smaller and as I shrink this down and down and down. It has the same linear speed as well too, but as I shrink this down, any arbitrary amount of surface I draw in there would still have the identical angular velocity in there. The question being, when I shrink this down to an actual point, how do I retain that vector? And it's the idea of defining then this vector, right? This is a vector, and then crossing it with any, right? The vector product between these two would give you. I don't want to go over that. I mean, sort of just keep on going on this stuff. So just right. So we're at this point right now that angular velocity or angular momentum would I would be able to model that if I have this cross product with the v. Right. So what was rotation too? So any sort of rigid body rotation, right? It was antisymmetric. To go back. So the rotational part that we looked at in lecture 2 is this idea that if you looked at any infinitesimal rotation for any point, you would get some sort of rotational matrix, or these are called infinitesimal rotation operators. It's a completely antisymmetric matrix, and it swaps around the entries. So if I move so moving around then this linear operator is this effect right here. This. So it's hard to get at, right? But this, right? I think that if you shrink this further and further down, maybe just accept that right? The cross product awaiting some velocity vector. Velocity vector, importantly, is the effect of this rotation matrix being moved anywhere around in your field. So it's still, right, so the idea, right, it's still sort of you give me an x, y, z, and t point, and I'll spit out a vector. It's just that the vector I spit out has this anti-symmetry part to it. Right? The other important thing to think about these cross products, or the cross product, right, is there's a parallel nature to them. So if you have in your marble right here, here's this velocity vector right here. And here's a coordinate system that I've defined right there. And this coordinate system is undergoing some small amount of rotation, infinitesimally, right? So maybe it goes like there, there, and then maybe up. Three-dimensional, maybe we can see right there. Right, so the velocity, where the base of the coordinate system is originating from, is undergoing some small amount of rotation, and that small amount of rotation is characterized by this vector of the gradient. So then this would then, right, so in this, right, so then you could have then some vector that defines you have some vector then that also defines the rotation. So I'm running out of colors here. Right, so then there's going to be some, call it this. It's kind of strange. Right, Nabla operator, right? Some vector, actually it has to be the transpose of it. Don't worry. So then have some vector and then some vector right here. So vorticity is perpendicular to that plane. That's sort of the key of geometrically what this is also saying, that if I have this being this vector here, and then this velocity vector going to be right here, these will define some sort of plane right? And your vorticity vector is going to be perpendicular to both. So I'll go down. No. This would be the omega vorticity vector, where it is perpendicular to the velocity, and it's perpendicular also to this rotational gradient vector, or the transpose of it. So all right. Talks about angular speed, angular momentum, really just trying to write that down. So the point is then, this is what you want to do then. If I can just take the curl of the Navier-Stokes equations themselves, right, I could characterize the spinny bits of the fluid. So I just have to take the curl of my Navier-Stokes equations, and then I will have the vorticity equation, which is telling you about the spinny bits of fluid given any point in the field. Right? So this is a statement about linear momentum. This, which is not spinny bits, right? This is going to give us the vorticity equation, which is a statement about angular momentum. I think so. People have all kinds of statements about there. But again, that's right. Just getting at that, like, why on earth you have that r or the del cross v to describe something about the spin? Well, the idea is that you're trying to describe this spinning marble, but you're shrinking the sphere of it further and further down. But that vector never went anywhere. It had to stay there the entire time. something still stays after you shrink this surface further and further down, right? And that's the difficult nature of this type of thing. Right? If I were to draw any surface, let's say around here, I could define that vector, but as I go further, further down, that vector still's there. Ends up being the cross of this. You could also think about these arguments of just like how two neighboring bits are moving relative to one another. So this one could be rotating, right? This v could be rotating around here, and this one could also be rotating around there. And as they get smaller and smaller, these almost converge to the same infinitesimal points. So in the notes, I sort of show how by just using vector identities, it's not that hard to do. But so in the notes, I go like, I personally define that special script D operator, because then I just need to end up taking how that changes, and you use vector identities. The hardest one being that you have to convert this operation. This is sort of difficult to show, but this is not a math class. I'm trying not to make it a math class. This is kind of fun to show, kind of. Where if you can show how this kind of operation is equivalent to this operation, then everything kind of works out. Everything else is just, you can look up in a textbook. You show this by just doing it to any arbitrary vector. But no one, whatever. So you end up then with the vorticity equation. And when you get the vorticity equation, you just do this operation. And it has a pretty beautiful form, I think, to it, because everything's sort of still there. It also sort of highlights kind of, you kind of see how, I don't really kind of see the benefits of this stuff, but there are, certainly some, especially for inviscid flows. Okay, so then this is the vorticity equation. This is the material derivative, just as I said before. It's not script D, it's the regular material derivative right here, right? So this is that capital D dt material derivative, right? Right, it's this operator right here. Script D was just something I defined to just kind of show you how Navier-Stokes equations really are just conserving linear momentum, and all the nomenclature is kind of the same. You just have to deal with the fact that you're operating on this region of points and not a particle. So it's not difficult. It's calculus on manifolds, essentially. What's this bad boy, right? That's a strain rate tensor. Remember it? Remember it from long ago? So that popped up in there. This is just a vector identity as well. So there's some Laplacian of the vector field, material derivative. What's not in here, though? So what's not in here is there's no pressure term. Okay, this is sort of a big, almost false sense of confidence this equation maybe puts into people. But that is sort of a benefit of the vorticity equation. It doesn't consider any pressure terms. Why? Well, a pressure term acts on the center of mass of points. It's a normal force to it. So it's always acting at the center of mass point, which can't cause a rotation. It also just comes about, right? Because if you take the curl of any gradient operator, right? So the way I did this is you could just take the curl of that hydrostatic head, right? But this is always going to be 0, right? The curl of the gradient of a scalar function is always 0. Any function, right? So it doesn't have to be the pressure actually at all. It could just be an arbitrary phi, let's say. And you can show that just through the calculations themselves. But what is fascinating actually is this one fact that this is a very general statement that a lot of math has proven further and further on. Essentially, where this at, right, this goes from 1D, right, this goes from 1 dimension to 2 dimension, and this one bumps up even more. This is a specific case of something called a DRAM. No one one really cares. But I just think it's interesting that like you can see an example of something that's such abstractly that it's proven in that sense. Hopefully someone cares. It's interesting stuff, I think. All right, so the vorticity equation is important, though, because it has a bunch of terms that you can internalize then to see how does the spinny bits of the fluid move around, right? If you can imagine spinny bits, right? That is, if you look at, right, it's almost easier to see vorticity. It was one way to also think about this as well, right? How do you visualize velocity in a field of liquid? Well, you can put some particles of fluid in there, and you can see moving around tangentially. But also in turbulent flows, etc., if you have just a bunch of particles on there, you certainly see a bunch of spinny vorticity happening, or just spin in general is occurring right here. Well, that spin is transported via this equation. But, you know, that's this false sense of confidence, I think, because the V still pops up in there. Right? It's still, right, it's even in, it's really in the equation still, the V. So it's really an afterthought. Vorticity, I can't find a way to describe it without at least having some handle of what the linear velocity is doing. I mean, it's even in the governing equation, this V star here. It's even in here, it's even in here as well, right? It's in here too, right? The actual velocity field, or linear velocity field, is in this definition. So you have to get at what what the velocity field is first, you know, almost to really say some things, at least in this sense. I'm not quite done though. So what do we have here though? Now, so you can certainly interpret these types of things now, where this, right, so you have a material derivative, so this is sort of the this is the material transport. So it's either, if I look at a point, that vorticity could change at a point given, but also there's this movement occurring as well, or advection. So that's encapsulated by this term right here. The rate of change, right there, sort of the rate of change of a vorticity field at any point in the fluid. And what do you have right here? This term it's a rotational straining term or something like that. People have a bunch of different names for it, but it's a dot product. Is it a dot product? Yes. Can't be a dot product. Did I write that down? Oh yeah, because this is a matrix. This is a matrix. So then this term right here, you have your strain rate tensor here. So that's that idea of how the straining motions of any sort of element I have. So this could strain out really far this way or strain out really far this way, and that's measured by this expression right there. So that scales up then the rotation, right, the vorticity itself. So this term is this idea that how the straining motions themselves add to the spinningness, right, the spinningness of the fluid, right? And this has an extreme amount of strain rate on it. If these marbles after like 3 milliseconds become like, you know, strained to just this almost like oval type shape like that, this term is going to be really large. So that's going to scale up this term really well. How would that be, though? How would you get the strain rate tensor to be extremely enormous? Well, right, strain rates, really fast speeds are going to have to occur for that to happen. And then there's this term right here, and that's the idea that if you talk about rotations, right, the effect of a rotation is caused by what? An imbalance of shear forces. So vorticity can help you characterize the viscous effects a bit more clearly maybe than the linear velocity equation just because of that. Right? It even has the same form as the other one, right? This is still, by a vector product, you have the Laplacian of this. Before it was the same exact term. So what dropped out was the pressure. This is shear imbalance. So This is really measuring the net imbalance of shearing forces on the sides. Anything I want to say about that? Yes. Okay. So there's a lot of things that are going on. So if you have a bunch of marbles, right, in the velocity field, there's certainly other issues that come about. One issue right off the bat, right, is if this is a surface, right? Well, if you're on a surface, you have to then imagine that all these marbles are going under and above the surface, right? So if I have some surface element like here, this analogy of spin in the fluid would look like this. So this is the surface of a body, right, or a boundary, right? So the point on the surface has to obey no slip. So this idea that for vorticity to make almost kind of sense or rationalize it, you have to imagine that all of the field are just these little spheres that are just spinning around, or spinning around, but you're shrinking them further and further and further. Now, in the limit, as this becomes actually a point, well, the linear velocity on the surface has to be 0 by no slip, but you can still retain you can still retain some angular velocity in that point, right? So the point on the surface, the angular velocity doesn't have to be 0, even in the limit. That's still a vector that can exist on the surface, but what does have to be 0 is the linear velocity. That must be 0 because of no slip. But it's still sort of strange because it's just sort of a strange thing. I think it's extremely hard to visualize these vectors that represent spin as you limit down to nothing. Because there has to be, the only way to measure, it seems like, the only way to measure any amount of spin is to draw a vector a little bit far away and see how that thing turns and turns around. But if you shrink further and further down, right, you don't have any actual distance to measure how something moves. But the idea that something sticks around, some vector sticks around, it's part of so many things about fields themselves. I mean, quantum mechanics has that issue as well. Maybe I can get rid of this now. So big sort of misconceptions, I think, is that while pressure doesn't pop up in the vorticity equation, it still affects it. Okay, right? So pressure the pressure still indirectly affects the vorticity equation. How could you always show that to yourself? Well, you can show that to yourself in the general sense. If you look at the most general vorticity equation, well, V popped up in there, right? And again, the velocity field is dependent on the pressure field, right? Force prescribes motion. So that means the pressure affects the velocity field affects the vorticity field. So in a chain of results, pressure does affect the vorticity field. How it actually does it is something we'll do later. But first, let's just keep looking at just this general equation. Right? This is the vorticity equation. It is the Navier-Stokes equations for this other field omega, which maybe you'll immediately forget after this lecture, which I don't care. Right? So let's do a scale where things are slow, or where things are pretty slow, or that this term is negligible. Right? So it's kind of hard to imagine, right? But the idea is like, what does this equation look like when v limits to 0 or is pretty small? But you have to think about the v being independent. Right? Very, very small velocity field. But it's hard because you go like, oh, but this was the curl of the velocity, so how would that go to 0 independently? Just does. Okay? It just does. Live with it. And then if it's 0 as well, then this term doesn't matter as well. It's hard to say that because hard to say that because of this gradient, so you can have a gradient B change. But again, so this term won't matter, this term won't matter, and then this term won't matter as well. Okay. So then in the scales here, we'll have then that the vorticity is going to balance this viscous force, right? Or viscous diffusion sometimes, right? Again, I went from material derivative to this time derivative, and now I still have this term retained right here. And I've done this by letting, right, sort of let's think about the average or vector magnitude of this thing go really, really small. I could get this balance right here. So no pressure, right? There's, in this equation, you see that there's really no pressure at all. And this looks like the heat equation. Okay, if you took heat transfer, you'd see this is right. The idea if I put an equal sign right here, right, the only difference is what? The difference is that this is a vector equation, and the heat equation is a scalar because it's for temperature. That's fine. So that just means that I just have 3 heat equations to keep track of. Nothing too hard about that. It's still all linear, so I'm still in the good. But applying a scale to this is pretty neat because, right, like all linear equations, things drop out. Okay, so then this would cancel out right here. And then you get this concept of a viscous diffusion length, something we've talked about quite a bit, but it's pretty direct from this vorticity view, right? So then you get the expression, right? And you've seen this before as well. This came up from what? Well, it came up from the oscillating plate. It came up from the impulsive plate. This idea that this mu divided by rho times some time value right here gives you this viscous diffusion. This is diffusion, right? The viscous diffusion length. Okay, so when the strain, right? So when the velocity is, when the velocity field is pretty slow, I have that vorticity diffuses somehow. It looks like, right? It looks like some diffusion of vorticity in the equation itself. So then by a scale, you can look at like what is, right? So as a function of time, what is then this diffusion length? It scales up by this physical constant right there. Right? Importantly, it just comes from the fact that a simplification of the vorticity equation kills a term. I get a simple linear PDE. I run a scale, and I can go like, this looks like, and it is, right? It's my viscous diffusion length as a function of time. So as time grows, right? As time grows, the viscous, right? The effects, the length where viscous forces are mattering, measured by vorticity, is growing kind of slowly, because it's a square root, so large values of time are killed. Right? And this is pretty general, right? This is a more general statement, right? This is a very general statement about this because it comes from a general three-dimensional balance. All it requires is that the slows are extremely slow, and you really show that through the linear momentum equation as well. It's called Stokes flow, where Reynolds number is basically 0. But this is another way to say it, right? Diffusion, vorticity diffusion. So how far does vorticity diffusion go in? Okay, can go a little further, right? So So even if it was a point, this would still work as well. So vorticity diffusing away from a point, you still get this relationship that it's dependent on this viscous times the time. This unit-wise work out as well. And you can do a little more with this as well, right? So you could do, it's kind of difficult, right? Kind of hard to appreciate this. Right? Taking a derivative of a scale balance is like quite a big no-no, but it works out in certain cases as well. Okay, so this is just taking the derivative of this. Again, you shouldn't always do this. It's kind of tricky to do that, but in these arguments as well. So then look at like the speed or the velocity of the diffusion length. That would be the speed at which vorticity is diffusing into a medium. And what is vorticity measuring, right? Vorticity is measuring the angular, right, or the shearing spin about particles, or about particles of fluid. So that is a measure of how viscous, right, how viscous forces are mattering because of shearing forces. Okay, so this is a sort of saying how fast, right, how fast does this viscous effects get into the flow itself? Okay, this is just by substitution then. Right, it's just just with this t is solve for t in this equation, plug it back in, and you get this, right, a velocity. So now you have a viscous diffusion velocity. This now, through the vorticity equation, we kind of see how the effects of viscous forces, how fast do they actually penetrate through into a flow, comes about from a scale of this in super slow flows. Right? So if this is a velocity right here, let's think about then that suction flow we looked at before, right? Remember we had some asymptotic suction flow where there were normal velocities going this way, let's say a v0. Okay, so if then that would be a velocity you could have, well then what's a good scale for this? So then it's just equating a velocity to this expression right here. Don't know why I did that. Sorry, I don't know why I put the square root over there. Don't put the square root over there. So no square root, right? So now if I have some normal velocity here where this is also sort of a viscous diffusion length, but I also have this asymptotic suction flow going up towards the plate because of a pressure gradient. Now even the scale of this lets me even calculate what the, right. Why am I doing that? Okay, so then solving here. So then in asymptotic suction flows that we had where there was pressure, we did it through a stream function, right? You got the same scale here, right? You calculate actually the viscous effect in your asymptotic suction flow is this ratio here, right? The viscous length. Okay, so viscous length scale and suction type flows. It all comes from just this balance of killing this term right there. And there's another one even for the stagnation flow as well. You get the same relationships. But you just get a lot of power in this vorticity equation for things like that. If I have slow flows, I just did a bunch of scale balances on terms, and I learned about the effect of a viscous forces, how far do those go in. And it's all based on this mu, right, this mu. Mu. It's all based on this new parameter. So I just re-derived a bunch of viscous length scales that you saw before, or a diffusion velocity. But importantly, if it's really, really slow, what it looks like then is that vorticity just diffuses. It looks like a diffusive process. Imagine if you put some amount of food dye in a bath and you just let it diffuse slowly throughout the medium. That's what the turning bits of fluid look like if flow is slow, or if viscous forces dominate. What else do we get? Okay, so then this vorticity straining. Okay, so vorticity straining is encapsulated by this term right here. So this is the idea of this. I have this, and then the matrix is a rate tensor and vector. This works out. So then let's explain this. Well, this is the strain rate tensor, right? So what do we have there? Yes. If you recall, this was sort of right. This is just a factorization of here, where I have the symmetrical straining or deformation parts of this strain rate tensor, and this is the anti-symmetrical part, or a thing that has to do with the actual rotation going. So then the stretching behavior is encapsulated right here, not this term right here. Even the units kind of work out the same exact way with this. But there's another way there's another way we want to do this part as well. And that's really looking at sort of this product right there. So then if this, you get this sort of magnitude of the vorticity, and then by decomposing it, you will have this. And I'll just try to describe this right here. I have to draw my picture as well. This is almost saying the exact same thing. It's just saying it for some point right there. This is just ways of factoring things out and seeing terms in some expression right here. But you almost can get to it just from the idea that this means a stretching rate. So there's certainly components right here as well. So this is going to be what do we have here? Okay, so this decomposition of just this rotation or this straining term right here is just sort of showing you that there are more parts to it than we thought, right? So the idea here is really the length of that vorticity, right? The length of this vorticity straining vector, the size of it changes based on the straining happening in the field. Where this term right here is talking about the stretching of lines, and this term right here is talking about the turning of the line. So what I mean by line right here is if I have two marbles connected, okay. Okay, so I have two marbles, one at P, one at P prime. Okay, so then I have two. This is alpha is going to be the vector, right? It's going to be the distance between these 2 points. And then D, this is going to be a directional as well. These are actually both vectors, so it's hard to see that. But and then this, right? If this is going to be my vorticity here, or the spin vector itself, right? This has some direction associated, right? Which is this d hat omega. So this is a directional vector telling you the direction of the rotation that's occurring. And this vector is a displacement vector between 2 points, right? So alpha that's what I'm trying to get at. That alpha is this arbitrary displacement between 2 points, them being, right, P and P prime. And then there's an omega, there's the spinny bit, there's a rotation occurring at P, or can you likewise do this the other way around? It doesn't end up mattering. So then there's a vorticity, or there's a spin of this marble, and that's defined by some vector with a direction to it. That's this term right here. All of this to say that, like, right, the size of this vorticity vector has this part A that corresponds to if this vector gets large or small, right? So if A, right, so if this term gets larger and larger, right, or any sort of change in here, so the stretching is something that's affecting it. that directly plays into the size of the vorticity vector. And then this cross product is also the spin, or the turn of this arrow. Right? So I just wish I had some sort of it's like this vector sitting in space of the vorticity. If I change the length of it between 2 points, now this had to decrease. Likewise, if I increase the vorticity here, if I made it up, if I turned it all the way to 4 markers, now this grows. And then there's the other part about this term right here, which is the spinning of the markers. So these could be at the exact same length, right? So this vector could just remain the exact same between p and p prime, but then this could rotate, and now this effect changes this vorticity vector as well. So that's how these strainings, or that's how the strain rate tensor in the field is changing the size of the vorticity field itself. And therein lies the rub, right? Because this vorticity field, you have to know the velocity field to, have any sort of description about it. Okay, now let's talk about vorticity at walls. I should leave this general equation up there, right? I need to get new markers. So vorticity, what's happening with the vorticity at the wall? At velocity at the wall, given to us, no slip. Always going to say it, experimentally verified. It's like the Stern-Gerlach experiment for quantum mechanics for fluids, I believe. Right? It's like the double slit experiment for quantum mechanics I think of as no slip. This experimental evidence that you have that you zoom in close and that fluid is not moving. Then people rationalize it later. It's easy to rationalize too. But at first it sort of wows me. Okay, so let's do this again where we write out the governing equation and think about scales to make some quantitative description about something going on. Okay. So here's the vorticity equation. It's got no pressure in there. So right, when I'm going towards the wall, let's say, here's some body I have, right? And here's just here, and there is some vorticity field. Right? Now imagine this equation, right, the vorticity. Do with this Navier-Stokes as well. Imagine that Navier-Stokes is some sort of tool that you can use, and it's like a lens. And you can move that lens anywhere around the field and magnify or zoom away from it. And what I mean by that is I can take this equation, and I could have it happen in this stage of my view, right? So here I would have a right? Sort of however you plotted your homeworks, right? And I zoom my mind's eye around here right now, and I can even change the aspect ratio of my camera. But all that must be true is that whatever's happening on the inside of the lens or the frame that you're analyzing is obeying the vorticity equation. Okay, so then what do? Well, then if I want to look at what's happening right on the surface, I take my lens and I zoom really close into the surface right there. Now, the same things hold. I know that vorticity equation happens in this viewpoint, in this mind's eye view. The only difference now is I've changed my aspect ratio of my lens, my mind's eye. So if I zoom really close into here, I'll call this, right, some length scale, usually with a y. Right? The tiniest length scale is getting smaller and smaller in my zoom field that I'm talking about. So what does that imply right here? Well, some people, right, so if you look into a, so the idea is at the wall, v has to be 0. So that's one thing you can do. What happens there? well, you get that vorticity diffusion equation thing that we get right there, right? The other way you can think about it, though, is also that my tiniest length scale has dropped down to 0. So now just look at this. We have a omega t, and then I have this omega vorticity straining rate. OK, so here's just all the terms I have right there. Right, gradients, what do they scale by? They scale by the 1 over your smallest length value, right? So now let's just go into a scale version of this, right? So here's the omega, here's some time scale, comma. I have some, scale velocity, scale vorticity, then some length scale. Same relationship in this scale happening. And here's where you kind of get the aha moment, is this, right? So in this equation on the scale sense, the dynamics that's happening right on the wall, right, the governing relationships that's happening right on the wall, really right on the wall no matter what the actual velocity is that's happening around there, okay, is governed by this. So as my length scale goes smaller and smaller, these terms don't matter at all. And then again, if you're looking close to the wall, I can pick a time scale to balance that as well. So I could make these balance, right? So clearly, just by zooming in on the scale, this L became really, really small, right? So this is okay, so I can have 1 match 4 just by picking a time scale really, really tiny to match it. But these ones I can't do that with. You would need, yeah, I mean, even and this is right, even in your idea, you can even think of it this way. Even as the u, right, you can't have the u being bigger and bigger and bigger because it doesn't matter. You're just going to zoom close enough in such that the viscous forces matter so that this has to be getting smaller. So even as big as u could be right here, it's going to get smaller enough eventually. And why is it going to get small enough eventually? Because we believe in no slip. So that's how this dies out. So that you say, at the wall, vorticity obeys a heat equation type diffusive process, right, from the scale. The other way you can do this same argument, I just want to do it right there, is you just say, you just say that the v is 0 at the wall, and then those terms die out, and now you just have these omegas. Everything's a vector. That's cool, right? So at the wall, the vorticity diffuses. It's a diffusive process. It's a vector valued equation, right? So while it's not exactly like the heat equation, in reality, in your head, you just go like, I just have to keep track of 3 heat equations. They're linear, not that bad. Very, very doable. Very doable. You can program it. I can program that by memory now. It's actually how I judge the speed of a language as I solve that equation in a 2D domain. Julia's really quick. OK, so do I have anything? I think I am losing things. This is what happens when you don't number your pages. Yep, this happens when you don't number your pages. You look like an idiot. But I'm going to cut this out later, because I'm going to be an editor. That's how I know to cut. So, right, at the wall, that's the governing equation. But let's step back. Let's step back a bit, and now let's look at the momentum equation. So now we jump back to Navier-Stokes equations. When you do vorticity arguments, it seems you always have to do this to jump back and forth, right, the real Navier-Stokes equations and then the vorticity equation. So as much as maybe people think it's interesting, I don't like the vorticity equation. I tried to. I really did. Maybe it's a turbulent thing. Even turbulence, I think you still need to, never mind. Okay, so same arguments apply. Same arguments apply. And that's the same way, that's why I did this scale thing right there, right? Because in the linear momentum case, you can't say, right? The linear momentum case, you're going to have a hard time getting rid of that thing if you said it was 0, because then everything's just 0, right? You just have pressure balancing nothing. But in the scale sense, these are certainly the two, these will be the two terms that matter, right? At the wall, right? Why does the pressure term stick around? Anyone? Bueller, Bueller, Bueller. You can't scale away pressure. You can't have motion not balanced by some pressure. What do we have? And then this comes with the no-slip boundary conditions as well. So by a vector identity, though, this is also this. I'm not going to show vector identities from you. I think it's a lost art. Vector identities. Feynman loved vector identities, and then people started using tensor notations and integral notations. I think that's because they're easier to code and implement in a computer, but I think they're horrendous garbage, and it loses the geometrical interpretations of some of these things. But you can do like diagrammic notations for tensor integral notations, and they can certainly tell you some things. But even that, I don't quite believe it. I think I use symbolic notation because it's easier to rationale things instead of just like a bunch of indices. Some people aren't like that, so let them be. Let them be. Here's a negative. What's this, right? So now you have this. You can move over. I mean, it's really. I mean, you could say inequality, right? You could say inequality just because of a different version that like. Right. So then here, what do we have? This is another way of like a dual version of thinking about the vorticity equation is going to the linear momentum equation, balancing, having this length scale drop down to 0, retaining a pressure term because it has to be there, and now you get this equation. So now I have two ways of looking at the exact same thing. What does vorticity look like at the wall? I think this is beautiful. You get a cool, right, sort of scale when you do this. Where these are components of the vorticity. Stick with me. Okay. By the way, I'm talking about pressure now, not linear momentum. I can't be talking about linear momentum with that p because linear momentum has to have a vector on top of it. Pressure is a scalar. But again, this p does not mean linear momentum. I'm talking about the actual pressure of our equations of motion. Okay, so I'm putting up now all of the components. Okay, and this is just this relationship right here. Again, I've just moved this over the row because it didn't really matter. You only need to keep this. Never mind. Okay, so I've multiplied through by the density to now put that back into the mu that you're used to. So I could do that. Right? I could have rho there as well. So this is a way of thinking about pressure. Here is exactly where pressure comes into vorticity then, right? Because you can see now how pressure gradients cause some flux occurring of vorticity, right? What's another thing to think about this vorticity diffusion is there's another equation that's too happening right here, and that's that vorticity also obeys the solenoid field, right? Some people call it like that, right? Vorticity also obeys sort of this continuity equation that you're used to. And that's via the definition as well, that the divergence of any cross product is always a 0. It doesn't actually matter what the v is. Sort of think of this as being the 0 operator. Again, these are specific cases of something called a Durham cohomology chain, which is amazing to me. It's been proven for all n dimensions that the n plus 1 dimension operator by the n, right, the n plus 1 by the n is the zero operation. So you saw the same thing. Remember I took the curl of the pressure gradient and I said it was 0? It's the same thing as the divergence of the curl is also equal to 0. just in an operator sense. So then, okay, I got some relationships here. And I'm looking now at my y-coordinate at the wall. So at the wall, right, I'm zooming in, and I'm going to have some streamlined coordinate against my surface. I'm going to call that y, and then I'll have what I write here. So this is going to be my x, and I'll say this is z. So it's a streamline. It's on the surface. You also think about y dropping closer and closer to 0 is the picture I'm drawing. So I'm thinking about vorticity at this wall, and we can see that the pressure gradients are somehow affecting fluxes, right? A component, right? The change in here as I change through here. And all of this is occurring, sort of think of this equation at y equals 0. All right. Now, one thing to always think about is when you have this type of equation right here, you've got to remember that continuity, or this, or the vorticity continuity, helps you determine relationships amongst components. So just think about here. Okay. So, right, integrating this equation, right, you get this. And this is really your at-the-wall conclusion, at least get right here, is what? Right here, using this, you say that, right, at the wall, right? The y component of this vorticity vector is 0, or the normal component out the wall, the flux, right, that value has to be 0. And that's by integrating this value right here. And as I make y 0, the integral of anything in the interior, if I go 0 to 0, that has to be 0. And it's a property, right? I mean, you can show that to yourself. If I integrate something from 0 to 0, there's no room in this space to integrate something, so it has to be 0. So one thing from here is I get that 0. Benefit here is you get what? You can zero out a bunch of things, right? So this was 0, 0. Everything. Okay. All right. So these are the interesting ones, though. Why? Why are they interesting? Well, as you notice, what is this side? So what is this side? Well, this side, right, is the z component and the flux through the wall, right? So this is the change, right, the change in the z component as I go out of the wall this way. And this is the change in the x component of vorticity as I go, right, in the y direction as well. So I have two components. I'm looking at the flux through the wall. So this is the exact idea that you have these marbles spinning in plane with your surface. And what do you show? You need to have pressure gradients along the surface to have vorticity. That is really the concept that you get across with this. This is where pressure actually affects vorticity. So this is where boundaries, right, are sometimes called right, they have vorticity production at the walls. See what I mean? Is this clicking? Maybe not, right? The idea that the pressure gradient in the x, right? If I have pressure gradients across the surface in the x direction or the z direction, right? So some pressure differential in x and pressure differential in z. We call this as a streamwise body type thing. So I have, right, some pressure gradient across this surface and across this surface. That creates some flux now of vorticity. Essentially what this is telling you is that pressure assigns the boundary conditions for the vorticity equation at the wall. I will say that, I can say it again, right? Okay? This is what the vorticity equation looks like at the wall, but it needs boundary conditions. Turns out the boundary conditions have to be fluxes. They have to be a derivative, a slope condition. Right? So, right, I have three, this is that I have really three going on in this equation at the same time. But the thing is, what you end up setting is, this is only one component, but and there it is. That is where pressure actually is affecting your vorticity equation, is at the walls. There's streamwise pressure differentials across streamlined surfaces. That assigns your boundary condition to the vorticity equation. You run it forward in time, and now the pressure differentials are causing some vorticity diffusion, right? So this having some value right here, or there's some flux of vorticity through this surface, right, means that there's some diffusion happening. So this is the saying. Pressure gradients on the surface, streamwise, right? There's no one in the y direction. There would be if there asymptotic suction, but we're not having that right now. That's this idea, right? That because there are pressure gradients along the surface, I mean, if a body's curved, there's some amount of pressure that's being changed. I have a flux of vorticity. That means the wall has some diffusion of the vorticity goes through the wall, right? The spin nature of the spinning nature of your fluid of your velocity field is caused by a flux of vorticity through the wall. It's purely imaginary. I think it's really hard to understand it itself, but you will hear people talk about vorticity production at the walls, and that's what they're saying. Vorticity production being that there is some streamwise pressure gradient along streamline pressure gradient along your surface. That assigns a boundary condition to the governing equation, and that causes a diffusive process of this vorticity field through the surface itself. Okay, so I have some summary thing right there. I don't care. Now let's get to a wing, I guess. This is kind of, I guess, the neatest part about vorticity. There's other ways to really describe this as well that I think of in the velocity field, but vorticity and the spin nature of fluid helps for completely three-dimensional flows. But big picture-wise, you get this vortex of a wing happening. Okay, so if we do a two-dimensional flow, important things about vorticity. Two-dimensional flow only produces, right, the vorticity in the z direction. So if this is x and y, right, vorticity is only in and out of the board. Right, so this turns it into just some scalar thing you track because it doesn't really matter. You know that there's only one vector that's assigning the vorticity, so you don't need to really solve for what the components are because you know it's always in the z direction. It's always in and out of this board. Plane. So that's a benefit of vorticity as well. If you're in a two-dimensional flow, vorticity reduces the amount of field equations you need because why? Well, because in a 2D flow, you need to solve for u and for v. If you look at it in a vorticity sense, you only need to solve for a scalar function, really. It's just the sign of which telling you the direction. So for an airfoil, you get this situation, which we can analyze. All right, so I have this graph that I like to think of that. So I'll draw this graph first, and I'll show something that maybe is a description. Maybe you don't care. It does answer. I thought about airplane wings a lot when I was making this lecture, and I was just trying to answer some questions of why does it do that? I have reasons for that. this. Okay, here. Negative vorticity. This is what this graph is going to end up looking like. Okay, so if we go back to this pressure gradient assigning some flux of vorticity, right? You had this. Pressure gradient assigns a value for the slope at the surface. Okay. So we now can do a little bit of rationalization going on right here. Here's some stagnation point. Okay. So at this point, stagnates down all the way to v equals to 0. And then what do we get? Well, then you have this partial, where you have this part going over and above. So let me try to get this just right. Okay, so here's wing line foil. Let's have some sort of half body right here. So let's say maybe it looks a little something like that. And we did this with ideal flows as well, too. So maybe you can go back and look over there just for the idea of what the pressure gradient along the surface is looking like. So really, I should have an S here, actually, not a X. So let's say S, where this is a stream surface coordinate, let's say. So over here, I have a negative pressure. Why is that? Well, because you have some layer occurring where flow goes in here and then must accelerate. So this is accelerating flow. And then on the other side, right, and then I get past a certain point, positive gradient. This is a decelerating flow. Accelerating. Decelerating. This is happening on the top. So on this graph, what I have, I've swapped it actually because of this negative part right here. So here's the top, and this is the bottom. So what I'm talking about right now is the top of this airfoil wing surface, so I'm now talking about the bottom of this graph, okay? So pressure gradients assign boundary conditions, so let's think about this in terms of flux right now. Make my dp dx really a dp dz. What's happening then? Well, I have this negative pressure gradient assigned as the flux. So that means at this stage right here, I'm dumping negative vorticity into the flow. Already this stuff's crazy. It's like we dump vorticity into. But hold with me, it's just kind of nice idealizations. So as the pressure gradient's negative, that gives me a negative boundary condition or a negative flux occurring for my vorticity equation at the wall. What does it mean? It means this pressure gradient, which is negative right here, such to have accelerating flow, means I'm dumping for some amount of time some negative vorticity value into the fluid flow. So that's this growing nature right here. Eventually, it reaches some minimum or critical point, right? Because I've gone from negative to a positive value. You know you go to a positive value because of the curvature, right? Because of the curvature happening on there. So that means at some point there has to be some minimum point right here. Okay, this is S. So if there's some point, it has to be some point right here. This would then be dp ds at S bottom star. So critical point right there. Okay, I've gone from negative to positive, so there has to be 0 in between there. So there's some special point right there where it'd be 0. Now it changes. Well, now the vorticity equation, if I go to the boundary condition assigned to the governing equation, what does it say? It's saying, oh my god, I hope I'm recording. Yes, I am. It's saying, right, now after I get back to this, after I pass this point, now I start sucking the negative vorticity away. So at this edge of the surface, it acts as if it's just pouring and dumping negative vorticity into the flow field. And then when I get past it, I start sucking that vorticity in. Whether or not you can rationalize or see vorticity in your head doesn't matter at this point. Just maybe understand it from a purely boundary condition aspect, right? The idea right here, so measuring negative vorticity, at this part right here, I'm dumping a bunch of that negative vorticity into the flow. After I get past here, I'm sucking the negative vorticity back into the surface. And that's what this graph looks like right here. Now on the bottom, there's a different curvature to this airfoil. And that's really by design, and that's what you see here. Okay? There is more of a curvature to happen. There is more of a curvature to occur right here. So this immediately jumps up. This essentially you see more. You see less of. You see a sharper curvature here to cause for a rise, and then a slow, smoother drop off in the negative direction. All these things really just to describe the same thing happening, which is a top star. And now what changes here? The thing is, what changes here is really just the algebraic sign of the s coordinate. So now, as I move down here, it's really the same thing, right? It could be like right here. Okay, same as the analogy. All that's now swapped is the direction or the algebraic sign of the streamline coordinate. So now on the bottom part, this is bottom right here, right? I have this accelerating flow. I have this accelerating flow downward, so the negatives cancel out here. So now I have a negative, negative, right? So now I have a negative, negative. Now the boundary condition is I'm dumping positive vorticity in, right? So there's a flux of positive vorticity happening in the frontal edge. And then essentially as I go back, I'll get slower flow as I go. I'll have a slower flow as I get back here, causing a decelerating flow. So now there's a different ST. The difference of these two pressure points right here, or these critical points where there's a change in pressure, is a function of geometry, right? All of this to get at one point right here is the difference in geometry or the shape of these foils cause the vorticity as it travels along all the way down there to have what? To have net vorticity. Right? So it's really, having this net vorticity at the end then gives you some spiral occurring at the very back end of these flows. There's some vorticity that must be conserved right there. And this is really what's producing the wake you see behind an airfoil. Because at this point, you have a discontinuity in the vorticity field. That's the problem. But what occurs there really is when it gets to this point of discontinuity. I mean, think about it right here. right? What the problem with this rationale in 2D flow is at this point right here in the velocity field, you are assigning now two different values for the vorticity. So that's discontinuous nature in there. But what happens actually when you get to this point right here, I think we all understand, is now the other dimension opens up to take in some of that vorticity. So it's no longer actually a 2D problem when you get right down to here, and that's where a wake occurs. So then you have this wake producing at the end or the back end of the airfoil. Okay. Sort of the idea of a wake forming is really an idealization of something happening where at that point something changes in the assumptions, right? So at this point, what ends up happening is this d by dx ends up blowing up to infinity. So now the physics have changed. So right now vorticity in another dimension ends up mattering a lot. So, I don't know, neat vorticity lets you describe that. There's one other thing. What am I time at? Whatever. I'll cut down later. So the other thing then with vorticity is, with viscous stuff, you've seen that, like, well, when I'm close to the wall, I can rationalize vorticity with this flux of vorticity through walls. Or when length scales get small, it looks like a diffusive process. But the other side of the coin then is in very far field flows, or when the straining rate of bodies matters most, and that's ideal flow. So vorticity equations still are neat for that, right? And these are the laws of Hemholtz and Kelvin. And I'll probably just state them, and then, because they're helpful. I won't have you solve vorticity problems, but understanding what these laws say are maybe helpful to rationale, like why you see things in fluids, essentially, right? So the first of Hemholtz laws, so this is Hemholtz. So the flow is really an inviscid type of flow. Anyone see a problem with this idea of inviscid flow? You should, that definition. What was that definition of inviscid flow? What's going on there? And it works out, right? So you have the singular nature of this type of a flow, where vorticity is confined to it's confined to infinitesimal lines or things of zero length. Okay, so the laws really are and that's this idea that a particle that initially has no vorticity doesn't gain any vorticity in an ideal sense. And this just comes from if I have some sort of let's say a vortex line. They're similar to streamlines, right? Similar to a streamline, we call it a vortex line. Okay, So in my field of flow, if I have something like this, and I start off here, right? So if I start here with the vorticity going to 0, the equations really tell me, right, that this is 0, starts off as 0, right? This is really just the law saying that that means, right? That means at this point, at a later point right here, that's what the statement is saying. So it's some sort of vorticity line or loop, right? If it starts off with 0, it never gains any vorticity. What next? There's a second one, second law. Hemholtz law. And that's just the elements of one vortex line or loop stay on that loop. So in terms of a loop, if I have some closed loop in a field and it has some vorticity over there, right? So here's some loop I draw in the vorticity field, right? Nope, doesn't intersect. This second law is saying if a bunch of particles are drawn in a vortex line and then process happens or motion occurs in an inviscid flow, that same set of points is just transported along due to the inviscid flow nature. So the second one is saying if you find a loop of spinny gas, if you find a loop of vorticity in your field, and then it inviscidly flows through, and then it inviscidly flows, they're on the same line again. And then the third one is sort of another neat sort of conclusion, and that is that a vortex line or loop it must be a closed curve or meet the boundary at both ends. So what does this say? It says, well, so for some type of flow that looks like this, let's say, I can have some vortex line that looks like that. That's OK. I can have one that looks like this. That's OK. But what I can't have is this. Can't have the ends of vortex filaments must meet at the ends of something like that. It must meet either at the boundary, must meet at boundary points, right, or be closed loops. And this is exactly really the statement of that diffusive process, right? So one generation of one place where vortices can be generated from, we already showed, right, was at a boundary. There's a pressure gradient in the streamwise direction, so I can generate some vorticity that way. It's basically what's happening on this idea right here. The fact that they connect is a reason of the inviscid flow nature. But the other way is you could just have vorticity in a loop, right, and it doesn't have to come from the boundary, but that must be some sort of closed loop is the major conclusion from this. What else do we have? Kelvin's theorem. So I should have put 3 over there, OK? And then there's also Kelvin's theorem, which somewhat's a little more general, I think, because at least it includes viscous forces. And that's this idea of what circulation is. So if I have some loop, right, that's happening in my vorticity field, Okay. Right, so there's some so there's a bunch of some vorticity field happening all around here right now, and I just draw some loop in that space, and I don't label my pages, so I awkwardly get lost. Well, then you're embarrassed. Okay, so then you have some space happening. This is a vorticity field. I just draw some loop. Okay, and then you have this circulation defined. Okay, for all x, y's, and z's that belong on this curve. So this is some closed curve. I'll call it C. Be parameterized by anything you want. So then, right, there's a circulation involved of this closed loop that comes about from integrating that loop. There's a velocity field tangent. So one thing about, so this is just definition of what we call circulation. I just have some sort of loop happening. I have some sort of loop that's occurring, right? And this is happening in some space. By a vector field, I have integrate this with vector field tangent. So then there are tangents to this loop, right? This tangent being defined in terms of the curve, right? Remember when we did streamlines, you can just think of a curve being some c of x and y, right, equaling some z. Always think of these curves. Just think of a circle. How do you write a circle down? X squared plus y squared equaling r squared. So that's what you have to think about what these curves are. Well, to get tangents on that, you do the streamline thing, you get a tangent thing. So that's how you can get at this tangent. Velocity field would have to be given to you, though. But having all of that parameterized, you could do this integral. The other way to think about this is using the Stokes Theorem. Where if this is a one-dimensional integral, you can bump it up to the second one, an area integral, but then you have to do the area derivative with a curl, right? So this is just really divergence theorem again. Okay. And then you can go, well, that would mean then that d sort of infinitesimally, though, right? So if this shrinks further and further and further down, right? Now I have one. Now I would have then one normal vector to my loop. If I shrink my loop smaller and smaller and smaller, like my marbles, right? Then I would just have one vector here defined by my shrinking element of area, and that's where the vorticity comes into play. Okay? It starts off being related to the vector field v, but then if I limit down my area smaller and smaller, right? Now this n becomes better well defined, and this is just the definition of vorticity. So the change in circulation per unit area, right? So if I just think of this quantity circulation, right? The change per unit area wherever I'm in my field is related to the vorticity field now. So I've decoupled this velocity. All of this really to just get at another relationship to talk about vorticity, not talk about the velocity field. But at every step, I hope you appreciate that you always have to invoke the velocity field to make some sort of statement about vorticity. It's not independent. It's not some glorious thing that fixes all of your problems. I haven't found it to be that. I can't really find any examples where it is. I just like the velocity field, honestly. I think it just really does say everything. I don't really know why people... But, no, it's kind of cool. So that's d by t. So Kelvin's theorem talks about circulation. It talks about how any circulation loop that you have, you draw in the field. This is what Kelvin theorem says. Notice it's a material derivative. Okay? So Kelvin's theorem is talking about this circulation that's happening on the inside of any loop that you draw. What does that say? This is sort of really similar to related to the third Helmholtz law, but it's saying, okay, if you have some sort of loop right here, it starts off as a circulation, right, as a function then t and t. So again, I can think about circulation now in terms of points, not areas, because I could limit down my area to be smaller and smaller and smaller, such that I get one point. Okay, so then flow occurs. Right? The change in this, right, the change of this circulation loop, right, the changes due to the transport, right, are the result of this viscous term integrating over it. Okay? So that's what this is saying. So now if I have another one here, right, the loop had changed some amount, right? The loop is advected and it's changed and it swirls around, et cetera, et cetera, et cetera. But however it changes, it's prescribed by this viscous term right here. And this is a closed loop, right? So if this is going to be c as a function of time, let's say. So here's my curve, but it could be a function of time. So think about the loop itself being some changing loop, right? Some loop in time, right? Parameterized by time. Integrating that for every element of time, right? I change then. But importantly, Kelvin's theorem does most importantly work for inviscid flow. Because if it's inviscid flow, you think of this being 0, or you have, right? Or you have or you have an ideal flow, it goes to 0 as well. Okay, so then you get this, right? So for ideal, here's the law. There's no, right? So the circulation constant throughout the transport of an inviscid flow. Okay? So this means that if inviscid, that means that right, it's constant throughout the inviscid flow. That's what the Kelvin's theorem says. It's a statement about these little loops that you draw in your vorticity fields. So this is interesting also, again, for this idea of accelerating wings, which is something that you can do. I used to do it as a kid, too. I had this little plane toy, and I had like I forget what it was, but it was like a little tub or something, and I remembered as a somewhat early memory, right? If I was a little kid and I had this little plane, I looked at it this way, and I moved the plane wing, right? So I had this sort of wing like that. Doesn't really look like that. And I was sitting in my bathtub. You had all these bubbles sitting around there, right? So it's sort of like it's sitting in this field of visualized flow, where on the top of the flow, I just have all these bubbles in my little kitty bathtub. I was a kid and I was stupid. I move this forward. You move this forward a little bit. So now, after a little time t, time a delta t. Oh, that's different. Now I have this here. Trying to do this. Okay, so starts here, t equals 0, and then over here. Okay, so what happened here then is some acceleration. You immediately accelerate some wing through some fluid, but what you see after you do that is where the wing was, right? You certainly get some swirly pattern that occurs, right? I think I drew the right direction. So maybe if you draw this picture right, you just, hopefully you just draw it. The idea is my little wing starts here, and I'm looking at it in the bathtub, but I go boom, and then where my eyes were fixed before, I now seem to replace this airfoil by spinning bubbles. Right? And it's sort of, where did that come from? And this is the idea, if you did it really fast enough, right, you satisfy this ideal flow scenario. And it's what usually you're really doing. I mean, for this, right, to not satisfy ideal flows in this situation, it's actually like you have to be pretty viscous and go like really slow, right? It's hard as a human to not do this, actually, just because your hands naturally move seemingly too fast for this. You'll always leave some amount of vorticity behind there because it looks like an inviscid flow. And that's what that's causing is what's happening is I've started off, right, at time equals 0. I had no circulation happening because I wasn't even moving, right? And then what happens is during this delta t, right, during this delta t, or acceleration point, I now created these pressure gradients across the surface. And what did that mean? Remember that these pressure gradients along the surface, what do they create? I'm dumping vorticity into the field for a small amount of time. Okay, so first process, no time equals 0, no friggin' circulation. Time equals 2, right? Or second point I want to make. Now, during this small time interval right here, I've made pressure gradients across my surface by moving it quickly through the bathtub. So now what happened there is it was no, and now pressure gradients they assign BCs to vorticity right? That's what they're doing. If you have small amounts of acceleration or small jolts in flow like this, 2D or even 3D, that acceleration or a small delta t of changing velocity is causing some pressure gradients across the surface, which assigns a boundary condition for what's happening at the very surface, which means I've dumped some amount of vorticity in there. So that small amount of time created then some vorticity and then created some spinning nature of the flow. And that's what you see right there. Because even as I keep moving far and far away, so now after a long time, let's say, okay, I'm trying to get this. Okay, here's the accelerating bit. There was a creation of there was some dumpage of vorticity into there from the surface of this foil. Okay, but then now, if it's now an ideal flow scenario like here, so then at this point I'm moving now steady in the flow. This still remained there. This is still hanging out there, and why that is directly because of the relationship of Kelvin, right? Because he says, for this whole flow scenario, I'm going to take this loop. Okay, here's now my closed loop that I'm going to integrate over. Well, in this sense, right, this is the idea that there has to be zero vorticity in there. So this vorticity that you see right here the circulation of here is exactly opposite to the one that you create on the airfoil. So this accelerating airfoil, you can replace it by a vorticity going the other direction of the same magnitude. So no more airfoil, actually, in terms of this this ideal flow scenario. All that matters is the little changes in velocities. The little bits of acceleration for unit time, they create a little amount of they create a little bit amount of a vortex, which then must be balanced out somewhere else in the flow. So this has to be 0. Or this must be constant. Wait, so this is constant throughout the flow, right? Okay, so before I did anything at equals 0, it was 0. And then later on, my same loop has to still equal 0. All I've done is I've stretched this loop out. So this is still 0, right? If this sort of minus this is 0. So you get these alternating things. You don't see this one. You don't see the actual vortex that you created on the wing from your impulsive motion. What you end up seeing is the reaction of that in order to satisfy this conservation of angular momentum. So I've gone over a lot, and I will put a disclaimer that you can skip this lecture if you want. Honestly, certainly some concept questions will be on the exam. I have no homework for Vorticity Viewpoint at all. If you're struggling, screw it, don't watch me. But you do have to get some sense of talking about vorticity. Because people like to talk about it, especially if you're in turbulence. I don't do a turbulence lecture, but the idea that a vorticity is describing how much of a rotation is occurring in this wild, crazy flow scenario, and the fact that it identifies where the actual viscous forces are being transported within the flow, it ends up being a good language to speak about fluids with. So I'll put a disclaimer, but if you did watch this, maybe it's just not scary to hear someone talk about vorticity anymore. You at least know what it is. It's a dual type problem. But most importantly, you can't get at it without the velocity field. It's a dependent thing on the velocity field. I showed you that with the pressure boundaries. I showed you even though it's not within the actual equation, it's manifested in the boundary condition for close to the walls. So that's the vorticity viewpoint. Notice I didn't solve any things, but we're kind of moving into just speaking about fluids now, so hopefully you all like me a little bit more. Next, though, is Jeffrey Hamill flow, baby!